Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So yesterday, Chandu started with in the introduction. He said there's no such thing as a stupid question, only stupid answers. I wasn't familiar with the only stupid answers part. I think that might have been Chandu's innovation. And certainly I made this very obvious yesterday. I got a lot of very good questions and I gave some very stupid answers. And so I thought, let me revisit some of the stuff that went on yesterday. So what was going on, and I'm going to pose this as a puzzle to you guys, is that I made some assumption in some of the answers, and then I dropped the assumption in some of the other answers. I made that assumption explicitly, though. I wrote it down. It was on the slide. I said it. And then sometimes I forgot about it. So there is a mystery assumption X. I'm going to have you at some point guess what that assumption was. So under the assumption, the replication protocols that I presented are in fact correct. Although the passive replication protocol actually does more work than it needs to do. But it works, as far, I think. Without the assumption, and I dropped it sometimes, the passive replication protocol is still correct, but the active replication protocol, in fact, is not. So the question is, well, what is that assumption? And again, so now I'm asking the question, and you guys have an opportunity to give stupid answers. I want to go back into that before I get into gossip. First of all, gossip is a bad thing to do. But also, Paxos doesn't actually use that assumption. And it's kind of interesting to see what happens when you drop the assumption. I mean, it also drops, Paxos also doesn't use accurate failure detection. So something that Paxos does in order to give you these consistency properties, it does it with way weaker assumptions than I was using yesterday. So, just to see what that assumption X does. So, before we go and try and answer that, although, if somebody wants to answer it already, go ahead. So first, very quickly, so virtual synchrony. Virtual synchrony is group communication. It's just a little different from the group communication that Peter just talked about. We've got processes executing in epochs. And each epoch has a view, right? The view in which it starts. And processes can only communicate with other processes in that view. And it simulates an execution that's indistinguishable from one in which no failures happen. And then at some point the epoch ends with a new view of the next epoch, and it is as if at that point some subset of processes may fail. It has to be a strict subset. At least one of the processes has to survive, because if all processes fail at the end of the epoch, you're left with nothing. So that's the virtual synchrony recap. And then we also talked about something called reliable broadcast, which is that if the sender is correct and some correct process delivers M, then all correct processes must deliver M. And the implementation that we talked about is quite simple. When a process simply broadcasts that message, and every receiver, when receives the broadcast, echoes that message to everybody else, and then delivers the message. Now, yesterday I said the other way around, which is actually wrong. I said delivers the message, and then it sends the echoes. But for, the way you would implement it is the right way. First you echo it, and then you deliver it, and that's actually important because that guarantees that those echoed messages are causally before the delivery. The local delivery of the message. So if you deliver a message, the messages will be delivered to the other processes causally before that local delivery. Okay, so something you get then is actually something a little stronger than reliable broadcast, something that's called uniform reliable broadcast, which says that if a sender is correct, or any process, it doesn't matter whether it's correct or not, delivers the message, then all correct processes must deliver M. And why is that? Well, if there's just set, the broadcast primitive echoes, rebroadcast messages before they're delivered. And so if a faulty process delivers it, well, the other ones are causally before it, and so the correct process must deliver M as well. So that will become important in a second. So then we talked about these two different ways of doing replication. One is passive replication, in which there's a single copy of a single copy of a deterministic state machine. It actually doesn't even have to be deterministic for passive replication. There's a single copy of a state machine. And there's a leader, and the leader orders operations, applies the operations to the copy of the state machine that it has, and then whenever it has updated the state, it broadcasts the updated state to the other processes. So you got n copies of the state, but there's only one state machine, like only one process that executes the state machine. That's passive replication. Now, I had in my protocol the following line. Before you send a result to the client, you have to wait until you have received an acknowledgement from all processes in the view. And I got various questions about that. Very good questions, and I gave various very stupid answers to that question because of this assumption X that I dropped in my mind, but in fact it holds. So this protocol actually works without this line in it. We don't need this line. You don't have to wait. After you do a reliable broadcast, you can immediately send a result to the client. And why does it work? Well, if the client receives the output, then that's causally after the sending of the result. Well, the sending of the result is causally after the delivery of this event. And in particular, it's causally after the reliable broadcast. The reliable broadcast will send everything to the other processes, and particularly the correct processes, causally before sending this event. So even if the leader is faulty, if the client receives the output, then all causally prior messages, according to the properties of virtual synchrony, all causally prior messages have to be delivered as well. Well, particularly the state update that was sent to the correct processes have to be delivered as well. And so we don't actually need this particular line. And so I gave the wrong answer to that. And why did I give the wrong answer? Well, so I was arguing when I got the answer, somebody asked, like, why are you waiting for acknowledgments? I was saying, well, here's the deal. Say that the leader replica here sends a response to the client and then fails. Then it's not guaranteed that the other processes have a copy of the state. And now the client has seen a response. The update is not persisted at all the replicas, and in fact, may not have been persisted anywhere. But it's not true. I mean, because it's causally prior, they have to be delivered to all those replicas. So there's an assumption I'm making there, and I don't know, maybe some people can already figure it out, that silently dropped when I gave you that answer. Now, an active okay, this already said, I think. So in what's happening here? Oh, I'm pushing the wrong button. How do we go forward? Active replication. Okay, active replication. Here I showed you active replication protocol. Now, yesterday after the talk, Rama gave me an excellent question. So there's something I don't understand about this protocol. So in active replication, you actually have n copies of the state machine. So it's called a replicated state machine approach. You actually replicate the entire state machine, not just the state, the entire state machine. And so you still have a leader, typically. And the leader, you send operations to the leader. The leader orders the operations and sends them to the various replicas of the state machine, along with a sequence number to ensure that every replica applies the operations in the same order and therefore end up in the same state. Now Rama said, what I don't understand, if you send a result here to the client, and this is just one of the replicas, when it receives an operation from the leader, it applies it and then sends a response to the client. What if that particular replica is faulty, and the other processes don't receive that message? After all, I had to define reliable broadcast to mean if some correct process delivers the message, then all correct processes have to deliver the message. Well, if the process is not correct, there's no obligation. Although I've just told you that, in fact, the properties are stronger. So with these stronger properties, even if a faulty process delivers the message, all correct processes have to deliver the message. So again, if the client received a result that must have been causally prior to this particular event, which must have been causally prior to, am I saying that the wrong way around? The delivery of the output to the client is causally after the sending of the result, which is causally after this delivery, which is causally after the reliable broadcast. And so every correct replica will, in fact, receive the update. I hope I got my answer right this time. So this protocol is, in fact, correct under the mystery assumption that I'm making, that I made explicitly. So, any guesses what that assumption was that I sometimes dropped and sometimes used? Yes, in the back there. I certainly used the property that messages are causally ordered. But that's not the one. I was making that throughout already. There's another one. It's a little bit of not a good question to ask, because after all, I stated that I was making that assumption. I mean, the assumption that I was making is that the clients are in the view too. It's not just the servers that are in the view, but the clients are in the view. If the clients are not in the view, then those properties of causal, causally prior messages have to be delivered, no longer apply. And the reason I was dropping that assumption, because in practice, clients are, like in these group communication protocols, clients are typically not part of the view. In systems like ICEs and trances and what have you, all these virtually synchronous computer systems, they didn't put clients in the view for the simple matter that it wouldn't scale. You had a service that had a few replicas, and so you put them in a group. But there could be, thousands and thousands of clients. And to agree on who exactly is in the group, didn't really, didn't make any sense. That was expensive to maintain because of this consensus property. You have to solve consensus every time a client joins, leaves, and so they didn't put clients in the group. So yes, here's that assumption that I made. I said that the process in view V can only send message to and deliver messages from members of V. Clearly has to include the clients. And so a protocol like active replication, in fact, doesn't work, at least not in this form, if clients are not in the view, because if the client receives a message, it's it's outside of the view. So this must be some kind of other, out of band type of send operation. Well, the whole causal relation is no longer tracked. Virtual synchrony only tracks messages that are sent within the view. This is outside of the view, and now Ram is absolutely right. Without that assumption, a client may receive an output from a faulty server. That faulty server may crash subsequently. The other processes may never, there's no obligation at this point that the other processes ever receive the message, because maybe the leader also crashes, and the protocol would be broken. And you would actually have to do something more complicated. And that's, what Paxos, in fact, is going to do for one thing. There's no assumption in Paxos that that there's any kind of causal delivery, in fact, let alone for clients. So I just wanted to rectify that, and I think it also makes an interesting introduction to the Paxos protocols and replicated state machine protocols that you'll see. But it's a very subtle thing, and the thing with virtual synchrony, you can sort of pretend things are not subtle, right? It's just there are no failures, and so you can keep your protocols very simple, and they work because you can pretend that all processes are correct. As soon as you drop some of that stuff, things get a lot harder, and when you'll see Paxos, you'll see various consequences of having dropped those nice properties. Any questions about that? Otherwise, we'll go. Actually, I have one more thing I wanted to mention, but no questions. Okay. So I just wanted to quickly talk about the various properties of broadcast that have now come up. I mean, yesterday I gave a simple hierarchy. Talking with Lorenzo, I mean, it's we talked about it. It's not really a hierarchy. It's really a collection of properties. And so there's a variety of ordering properties that we talked about: FIFO ordering, causal ordering, total ordering. Actually, we talked about atomic ordering, which was causal plus the property that all messages have to be delivered in the same order at the various processes. That you could actually separate. You could make something that's totally ordered, but not causal or FIFO ordered. So the ISIS atomic broadcast gives you both causal and total order, but you could have total order by itself. Causal order implies FIFO order, but mostly these properties are fairly orthogonal. When you look at reliability, which you can think of as liveness properties, or though in the world of virtual synchrony, they're actually safety properties, because they have to hold by the end of a view. But that's a detail I won't go into. You got these properties. So I gave you a combination of the persistence and the relay property. Persistence property says that if a process is correct and sends a broadcast, then all correct processes have to deliver the message. The relay property says if some correct process delivers a message, then all the correct processes have to deliver the message. So those you can combine into one property, like the one I gave you yesterday, which said if the sender is correct or some correct process delivers the message, then all correct processes have to deliver the message. And then there's something called uniform reliable broadcast, which says that if some process delivers the message, it doesn't matter whether it's correct or not, then all correct processes have to deliver the message. So that's a stronger property than the relay property. Okay, so that's the various kinds of broadcast properties that people talk about, and of course each one of them has a different implementation, and we saw a bunch of them. If you drop some of these properties or these assumptions like accurate failure detection, the protocols get harder, and Paxos in some sense is an implementation of an atomic no, actually a totally ordered, not an atomic one, a totally ordered broadcast protocol in some sense that, in fact, gives you uniform, reliable delivery. Okay, now we're going to start gossiping. And so I'm going to argue that some forms of gossip are good. I'm probably not going to cover all the slides that you got in your slide set. I will give you an introduction, say a little bit about the history, give you some intuition about how these gossip protocols work. And then we'll only present in the next hour one case study. I think that's probably all I have time for, but we'll see how it goes. So, introduction is, so gossip is essentially a form of data dissemination, like broadcast. But it looks a little bit more at a particular implementation of broadcast. So you want efficiency, you want robustness, you want speed, you want scale, all those kinds of nice performance properties. Now, tree distribution, Peter talked about this this morning, is very efficient. It's also very fragile. If a node in the tree fails, you have to reconfigure the system. It's, can be kind of tricky, and there's certainly a hiccup involved during which messages can get lost. So trees are efficient but fragile. Flooding is another way of doing it. In fact, you could do that probably on pastry as well. You just send it to all your neighbors. Like whenever you receive a message, rather than sending it on the tree, you just pass it on to your neighbor list, and every neighbor passes on to their neighbor list, and eventually the message will get to everybody. And if the graph is well connected enough, it's highly robust. But it's also very inefficient because a lot of processes will receive a copy of the message more than once. And then we got gossip, which tries to find a different point in the design space. So it wants to be efficient like trees. It wants to be robust like flooding. But it's not going to be as fast as these other protocols. And if you put that in a nice, here's a nice graphic where you see that trees and flooding are fast, trees and gossip are efficient, and gossip and flooding are robust. And there's a certain, a cap-like property to this, like with cap. That was talked about yesterday. You got these three properties that you want, but you can only get two at a time. Pick any two, but that's what you can get. And it's similar here. Like getting actually a dissemination system that's all three, efficient, robust, and fast is hard to get. So 2 out of 3, fine. 3 out of 3, it's complicated. There are trade-offs involved. Okay, so a little bit about the history. I usually don't give much about history when I talk about things because I'm always afraid I'll miss some people, and of course I miss some people here. But I could, I just loved the title of the first gossip paper that I found that I had to put a slide in. There was actually an MIT paper in 1972 that was called "Ladies and Telephones." And in fact, it looked at the dissemination of gossip in a telephone network. And for some, it's a sexist title, but there it is, 1972. It's not even that long ago. The more computer sciencey stuff came in 1987 when Al Demers, now actually a colleague of mine at Cornell, but then researcher at Xerox PARC, worked on the clearinghouse directory service, which was in fact an alternative to the domain name service at the time. It was the same time that the Internet Domain Name Service was being developed. And Xerox PARC proposed this other thing, clearinghouse. DNS won, but we could have had a gossip-based domain name system if they had been more successful. And then there's various things that came afterwards, including a bunch of projects that I've worked on. Now, there are two types of gossip. They're called rumor mongering and anti-entropy, and they have sort of different objectives. So rumor mongering is more like the broadcast primitive, but with sort of probabilistic properties. So basically, when you have a message you want to disseminate in the system, you give it to some of your friends, and some of your friends will gossip with some of their friends, and so on. And eventually, that message will spread throughout a population that way. And you do that for some time, and sometimes you stop because you can't gossip forever a message. And so there's a probability that not everybody gets it. The longer you gossip, the more likely it is that everybody gets it. And so there's a trade-off, and you can in fact analyze this thing, and it's very much like the same kind of analysis that you use for tracking virus spreading or something like that. So epidemiology. And then there's anti-entropy, which is not a broadcast primitive. It's more like a state machine replication-like thing. You're replicating some data, and you have an update, and you want to apply that update to every copy. Well, you keep on gossiping this update, and the updates actually have version numbers on them. And so, since you only need to apply, so for example, a key value store or something like that, you may timestamp the update. And so newer updates are obsoleted by older ones. And so when you start gossiping a new update, the old update just disappears out of the system because you're only gossiping the latest one. And that's good for state reconciliation. And in fact, I think pastry uses some version of this. So properties, the nice properties of gossip are that the gossip spreads, in certain sense, exponentially fast, like a virus or like gossip, and propagates in a time that's proportional to the log of the number of processes. It's very tolerant of various kinds of failures, be they message loss or crashes. Not so tolerant of Byzantine failures, by the way, but we're talking about crashes. And it's easy to model the behavior mathematically. Okay, so here is a gossip protocol. This is, in fact, let me see, this is an anti-entropy protocol. Probably most of what I'll be talking about is anti-entropy. So basically you got 2 threads running in each process. One thread that periodically picks a random process it knows about, a random peer in the system, and then sends its state to that process. And there's another thread running at that process, and then every other process, that sits there waiting for these gossip messages to arrive. And then when it gets one of these messages that contains, some state from another process, it merges its own state with that from the other process and updates its own state that way. So receives state, takes its own state, runs it through this merge function, and out comes its updated state. So for example, in the case of a key value store, the merge function would take the latest version of a particular key value pair. So how does it work? Here's a system with what, 8 processes? 8? Yes, 8. And in this case, it's a fully connected network, so everybody is everybody's peer. It doesn't necessarily have to be that case, but so one process has some information, a new update. We sometimes say it's infected, and so its thread at some point picks a peer at random and sends it its state. And now this peer is infected as well. So after round 1, 2 processes are infected. Now we got 2 processes that are infected and they're gossiping. So a round later, they each pick a random peer. In this case, they're lucky. They pick different peers. And so after round 2, we got 4 processes that are infected. Well, that can always go right, So at some point, they're going to pick the same peer. So sometimes, at some point, there will be some overlap. But nonetheless, after round 3, there's only one peer left. If we had been luckier, all peers could have been infected, and that's as much as I simulated this thing. I mean, it could of course go very badly too, right? You could have these. Why am I so bad at these? These two pairs could have been gossiping to one another by sheer chance for many rounds to come, and only after round 100 there could still be only two. And in the best case, it will take 4 rounds. What is it? 3 rounds, right? To infect all the members. So if you look at the function here, which I drew out of just with my hand here, but so if we have time going from left to right, like Lorenzo likes to have his time going left to right, and here's on the y-axis is the percentage of processes that are infected. Well, you get initially a sort of exponential growth. Then at some point, half of the members are infected. At that point, there's going to be, a lot of collisions where you're trying to infect members that are already infected, so things are starting to slow down. But eventually, all processes are infected. And now the question is, well, how long does it take on expectation? Actually, that's a question that I'm going to be talking about in a second. So as I said, the gossip message has the state from the center of the gossip, and uses a merge function. In order for this to converge in some way or another, we need to have certain properties of that merge function. Like, picking the latest update is a good one. It's sort of, always makes progress. But if it picks one at random from the, the 2 updates, it's this particular gossip protocol wouldn't do anything that's useful. So when you design the merge function, you typically want to have something like one state is better than the other state. So when you merge it, you get that the new state is better than the state you had, and it's also better than the state you received, or at least as good as. Okay, so this particular scheme is called Anti-Entropy. It's a so-called simple epidemic because we don't have any. Because of this fully connected graph. So how fast does that spread? Well, there's a nice big old. If you go to the library, I forget when it's published. It's old. From a guy named Bailey who looks at epidemics. And so when we first started looking into gossip protocols, that's the book we got out of the library. And there's a bunch of math in there. I'm going to give you some idea of how that math works so that we can get some intuition about how gossip spreads. So again, simple and epidemic, fully connected graph. Anybody can gossip with anybody else, and they all pick their peers uniformly at random. And so let's look at a case where we have a population of some size n, and k members are already infected. What's going to happen in a round of gossip? So everybody's going to gossip. What's going to happen? So here's that population of size n. Here's the set of k members that is infected, and in this case, 2 of those members gossip to the same probability. So what is in fact the probability that some member here? What is it? It's the probability that some member that's not infected is infected if k are already infected. Well, it's a fairly simple binomial types of thing. So the probability that some process is infected is 1 minus the probability that nobody infects any of these members, which is this simple formula here. And so then we can look at the expectation of how many members are going to get infected in this uninfected population here, and that's n minus k type times that probability. Okay, that's clear, more or less. So we're going to sort of now look at the gossip spreading in 2 phases. First, going to look at how long does it take to get from one infected member to half of the members being infected, and then how long is it going to take from half of the members being infected to all members being infected. So the halfway point, by the way, so if what's the probability, or the probability that some member gets infected, or that nobody gets infected. What is it? That some member gets infected. If half of the members are infected, is about 0.4. So at the halfway point, half of the members are infected. The number of members that get infected here grows by about a factor of 0.4. Okay, so in the first half, as I said, it goes pretty exponentially because the probability that two members pick the same other member is relatively small still. And so, at the very beginning, the rate of growth is 2 when there's only one member infected because it cannot pick itself. And then halfway, we just saw the factor is 0.4, so it goes from the factors 1 to 1.4. And so everywhere in between that halfway is somewhere, the growth is somewhere between 1.4 and 2. So it's bounded between 1.4 and 4. That's somewhere between that is the rate of growth. Right? It's not less than 1.4 because that's the halfway point. It's not more than 2 because the process is only gossip with one other member. So it can grow by at most a factor of 2. So, it's exponential somewhere. In the first half, it's definitely exponential. Now, what we do in the second half is sort of turn it around. We look at the rate instead of looking at how fast is gossip or are the number of infected members growing. I'm going to look at how fast are uninfected members declining. So initially, that's very slow, right? It's like we have n-1 uninfected members, and then it's n-2, and then it's either n-2, n-3, n-4. So it's pretty slow initially, but halfway, the uninfected population declines by a factor of 0.4. And then at the very end, when there's only one uninfected member left, the probability that that uninfected member gets infected is 0.63. Play the same game. We know that everywhere in between, it cannot be, well, it can be, but it's at least as good as 0.63, and the worst is about 0.4. So again, it's bounded then above and below. And so we still have exponential growth there. And so in fact, the number of rounds that are expected to infect the entire population grows logarithmically in the size of the population. And if you just do a little bit of simulation, you can see that the base of the log it's about 1.58. So it's that's the average growth across the entire epidemic. Okay, so it's still the case that it's logarithmic. If some of the members are not gossiping, if some of the messages get lost, of course the base of the log is no longer valid, then it gets a little worse, but it's still logarithmic. Okay, so here's some experiments. So here's some simple distributions. Here's the number of rounds that it takes to infect a population of either 64, 256, or 10,024 participants. And you can see that it takes about about 8 rounds to infect 64 participants, and then 12 rounds or something to do 256, and 14 rounds to do 1,024. So that's just this I actually just did a simple simulation of gossip to produce this graph. Ran a bunch of experiments and plotted the data points. If you then look at for many experiments what the expected number of rounds is, here's the number of participants on the x-axis, and you can see on the log scale that it's approximately a straight line. In fact, should be a straight line. Okay, so far I only looked at a very simple form of gossip, which is one in which the processes have some state, and then they give that state to some other process. You can also, and particularly that's an epidemic that starts very quickly, and then we saw that the probability that if the entire population is infected except for one, the probability that last member gets infected is only 0.63. It's not that great. Well, we can turn it around. We can, rather than sending state, we can pool it. We can, and it's our turn to gossip. It's my turn to gossip. I pick somebody at random, and I ask that process for its state, and pull it to me, and then I merge it with my state. So that has the sort of the opposite effect. Like when there's only one member that's uninfected, and it pulls from a random other member, it's guaranteed to be infected as well because all other members are infected. So it ends very quickly. But in the beginning, if there's only one member infected, the probability that that member doesn't get chosen is again 0.63. It has exactly the sort of the opposite properties. And so what people do in practice is typically actually combine the two. So whenever you gossip, you exchange your states. So when a process P gossips with process Q, P sends its state to Q, Q sends its state to P, and they both invoke the merge function. And so they both end up, hopefully, with the same state if the merge function is commutative. So that way, you start quickly, you end quickly, and the price you pay is that you send two messages in a round rather than just one. So it reduces the number of rounds, but it increases the overhead some. But still, this is typically the choice that people make because it's a good trade-off. Okay, let me have a quick look at time. How we're doing here. So still have 15 minutes, is that right? Okay, so maybe there will be time to go slightly into a simple case study, which is that of failure detection, right? So failure detection is a very important primitive in distributed systems. So far, I've assumed the failure detection is accurate. I'm going to drop that here. You cannot do accurate failure detection. But we can use gossip to implement a failure detector that gives you probabilistic guarantees about the accuracy of failure detection. And you can actually set that accuracy pretty much arbitrarily high if you like. So an accurate failure detector is impossible to build, but in some cases we can allow for some mistakes. I'm sure that the pastry system uses some kind of failure detector, and it must have some probabilistic properties as well. So various good reasons to have a failure detector, but the existing failure detectors, in order to be reliable, so existing failure detectors are usually based on pinging. You ping a process and then you wait. But messages can get lost, processes can be slow. In order to make it accurate, you may have to ping for a long time. And in fact, in industry, something like 3 minutes is not unreasonable. Wait. If you haven't heard from another process for 3 minutes, then you decide it's faulty. Because if you're faster than that, then a simple case of overload could lead to mistaken suspicions. And if you make it much more aggressive, set it to like half a second, you're going to make a lot of mistakes. So we're going to build one out of gossip that has fairly, nice properties. We're going to actually, have a constant probability of making mistakes. It's going to scale in the number of members, order n log n. The bandwidth is growing order n, which in the internet is fine. If you have n times as many members, you can use n times as much bandwidth. It's resilient against message loss and resilient against crashes. So how does this work? Oh, well, what's the environment? We have crash failures. We're going to allow partitions, actually, although I probably won't go into that. Message delay is unbounded. Clock drift is negligible. And the protocol is like this. So each member is going to maintain some state, right? We've got state. And the state that each member maintains is a list of all the processes in the system. So that has the addresses of those processes, the IP address, TCP IP address, and a counter, which I'm going to call the heartbeat. And periodically, each member increments its own heartbeat and sends that list to a randomly chosen member from that list. It looks at that list, picks a random member, and sends that list to that member. So far, so good? Good. So when a process receives one of these lists, it simply merges those lists. And so, how does the merge function work? Well, it looks at these heartbeats. For each member, it maintains so if you have two lists with the same address in it, you're going to maintain the one with the highest heartbeat. And also, you're going to keep track every time you see a heartbeat increase of the time at which that happened. So we're going to add some local state that's not gossiped, which is the time at which you see heartbeats increase. And so then the idea is simply, if you don't see somebody's heartbeat increase for some time, that's an indication of something not being good. So let's look a little bit at how this performs. So clearly the gossip message itself grows linearly with the number of members, because there's an entry for every member. And the number of members grows linearly with the number of members. And so we have a problem. If they all gossip at a constant rate, the bandwidth requirements on the network would grow quadratically. And so we actually slow down the rate of gossip with the number of members. And we have some bandwidth that we're willing to spend. It takes about 8 bytes to keep track of the heartbeat and the address, and so the time between gossips grows with the number of members. And then the other thing we need to determine is how long do we wait before we say, well, somebody's heartbeat hasn't increased for a long period of time. Should we report failure? So for that, we need to analyze the how fast gossip really works. I gave you a simple one before. I'm not sure. I don't think I really have time to go into details here. So maybe I'm going to skip that in the interest of time. You have a question? Well, it's a very good question, and I was sweeping that under the rug. The protocol actually allows these heartbeats to wrap around, so that we only allocate, I think, 2 bytes for a heartbeat and 6 bytes for a TCP IP address or UDP IP address. So that's 8 bytes total. Of course, after 65,000 increments, this thing will go back to 0. And so what we really maintain for each process is a little window, and see, because so to see if a heartbeat increases, sometimes it actually decreases when it's from going like around that point where it goes from a very high number to a very low number. And so we do a sort of a circular comparison using a window to see if a heartbeat increases. Okay, so I'm going to skip over the how we obtain these things and just give you some numbers. So we're using 250 bytes per second per member, so a very low bandwidth. And I picked that bandwidth so low so that the numbers are a little easier to understand. But you might, in practice, probably use more like 10 kilobytes per second. And there I have in the top of the graph three probabilities of making mistakes. Probability of making a mistake of 10 to the minus 9, 10 to the minus 6, and 10 to the minus 3rd. And so here I have the detection time. How long do you need to wait before you report a failure? And the number of members is on the x-axis. You can see that the failure detection has to grow as a function of the number of members. And so with 100 members, if you want to have 1 in 1,000 probability of making a failure, it takes about, I don't know, a little over a minute or something before you can report somebody as faulty. And if you want it to be more accurate, of course, you have to wait longer, or even longer, depending on how accurate you want this thing to be. Now that sounds, well, that's similar to what we had with pinging, like 3 minutes or something like that. But again, that's on a very low bandwidth requirement. If you're willing to gossip 10 times as fast, those numbers get 10 times better. Let's see, here's the quality of detection, the probability of making a mistake as a function of the number of members. I forget exactly what this graph shows, so maybe I'm going to skip over that. I'll get back to you on that some other time. This is a more important graph, actually. So the analysis looks at, also takes into account the probability of some members not gossiping because they're in fact faulty. And when there's a lot of members that are not gossiping, things have to slow down a little bit. And here you can see the effect of that. So the red line, so the x-axis is the number of failed members, and the y-axis is the detection time. That's the ratio. Q is the ratio of the number of members that are in fact not gossiping, that are faulty. And you can see that in order to deal with 20% of members failing, you actually have to wait longer in order to before you can report a failure, in order to get this constant probability of making mistakes. But it's fairly minor. Similarly with message loss, if you have message loss, you gradually will have to wait longer before you can detect a failure. And so this is the probability of message loss for 3 different numbers of members. Again, it goes fairly slowly as a function of the number of processes that are faulty or are not gossiping, or messages get lost. So that's where I'm going to stop for the break. So this is a very simple failure detector. You can the paper that I wrote on this subject also shows that if you actually use a 2-level hierarchy, things scales a whole lot better. But just to give you an intuition of how these gossip protocols might be used and how effective they are, I think this is a good example. In the next hour, I'll give you a much more interesting example of building what is essentially a key value store with gossip. But if there's any questions about this part, I'll take them now. Two. Yeah.
An assumption that you're assuming that the clocks of the system don't have a significant amount of skew.
Yes.
So where was that?
Actually, the skew is not so important. The drift is important. Did I say skew or drift? I meant drift. So because you need to measure time in this particular protocol. So it's all the calculations are based on time that has passed. But it doesn't require synchronized clocks. Sorry about that. Is there another question, or yes? Oh, yes. There.
In this, at the 0th point on the x-axis,
Yes.
the number of members failed are 0.
Yeah.
So what is the detection time for them? Like none of them has failed.
Oh, I mean, right. I mean, you could still accidentally suspect a member if something happens. So this is how long you wait when you. So if you wait for 100 seconds here, and you don't see somebody's, for example, Peter is in the list, and Peter's heartbeat hasn't increased for 100 seconds. That's pretty serious. But Peter might not be faulty. It may just be that gossip had a bad scenario, and that the heartbeats that Peter is gossiping don't make it further than, say, Lorenz. So Lorenz and Peter are gossiping with one another, but with nobody else. And so I may at some point decide that Peter is faulty after 100 seconds. It would be a mistake. And here we let's see. So here we don't have. I forget, there was some fix that's probably 10 to the minus 6th probability of making mistakes. At which point, so even if there are no faulty members, you still have to wait, and you still may accidentally flag somebody as faulty. Okay, well, let's take a break, and I'll see you in about half an hour, I believe.